Hello there, and welcome to this collection of notebooks and tutorials on advanced digital signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, and on this notebook we are going to talk about vector quantization. So in our previous notebook we saw the Lloyd-Max quantizer, and now we are going to extend the Lloyd-Max quantizer to a any dimensional space. So we're going to extend it to multi-dimensions, and we will end up with the Linde-Buzo-Gray algorithm and vector quantization. So on this notebook we are going to take a look at the definition of the vector quantization, and then we'll go through some Python examples to put vector quantization in practice using Iron Maiden music. So we're going to use the introduction of two Iron Maiden classics. So we're talking about Ace is High and The Number of the Beast. So we have this speech, the introduction of those songs, and we're going to use it for our examples. Let's get started. In our previous notebook, we saw the Lloyd-Max iteration that looked like the following. We would start our iteration with a random assignment of m reconstruction values, so code words y of k. Then we, using the reconstruction values, will compute the boundary values b of k as midpoints between two reconstruction values, so using the nearest neighbor rule. Then using the PDF of our signal and the boundary values, we would compute new reconstruction values y of k as centroids over the quantization areas. So it's the conditional expectation, centroid. And then we would go back to step 2 and update until we have sufficiently small changes that we define a value for epsilon. So this algorithm usually converges, so it finds an equilibrium and it doesn't change anymore, and it results in the minimal distortion d. That was the expectation of the error, squared error that we saw. So it's interesting to notice that this can be generalized to a multi-dimensional case, what is called the vector quantization. Scalar quantization usually makes the assumption that the signal to quantize is memoryless. So that means that each sample is statistically independent of any other sample in the sequence. So examples of those kind of signals are thermal noise, white noise, sequence of diastoses, lottery numbers. But many signals, they do have memory, so they have samples which are statistically dependent on other samples in the sequence. So for example, speech signals, pink noise, temperature values over ear, image signals, audio signals. And since many signals have this memory, we can take advantage of this. And one possible approach to deal with memory or to deal with these statistical dependencies in our signal is to use the so-called vector quantization. So how does vector quantization work? Instead of quantizing each scalar value, so each sample individually, we will group the sequence of samples into groups of n samples. And this way we are obtaining a sequence of blocks, so they are called vectors, of size n samples each. In this way we obtain a sequence of samples in an any-dimensional space. In such a way we can capture or use the memory between samples within each block or vector. So the resulting samples with memory in the any-dimensional space will lie on or near a hyperplane or a subspace within this any-dimensional space. So the good thing here is that we don't need to sample the entire space, but we only need to sample the part of our space where our samples are actually located. Let's look at this case when we take correlated samples such that one sample is always similar to the previous sample. So for example, a sequence of speech or audio samples. So usually we don't have very high frequencies there, and that means that the curve through the samples is more or less smooth. So now we will take the dimension n equals to 2, and we will obtain a two-dimensional vector space of samples, which could look like this. So we are taking these blocks with two samples each, Yeah, and then if our signal, for example, is a sequence with these numbers, we will get the following sequence of variables. So we're of vectors. We are having blocks of 2 samples each. So this is what we have. To take a look in a more practical way, let's go through a Python example. So in this Python example, we're going to use a LibRosa to load our audio files, matplotlib to plot, IPython display to listen to our signals, and NumPy for mathematical operations. Here is our signal processing parameters. So we are using a sampling frequency of 32 kilohertz, and we're defining a time vector of 1 second that we're going to use to plot our signals. So the first signal we are going to use is the classic The Number of the Beast introduction from Iron Maiden. So I'm loading using a LibRosa, then we're normalizing. I want to have the signals from -1 to 1. Then we're plotting here so we can see this is what it looks like, and let's listen to it. So now what we're going to do is to plot the 2-dimensional vectors with their sample values of even indices on the x-axis and their odd indices on the y-axis. So we have pairs plotted as a plus sign. So what we're doing, we're taking even and odd indices of our signal. So this is what we're doing here. And now we have 2-dimensional vectors, and we can see that they have this very interesting shape here in this diagonal. So this is the same signal, but we're plotting in a 2-dimensional space. Yeah. So since the odd and the even values are similar to each other, we get a distribution of vector points near the diagonal of the space. So we need to sample this space only near the diagonal. So more generally speaking, we should sample more densely near this diagonal. This shows that we need fewer reconstructions values or fewer code words as when compared to the 1-dimensional case, which means fewer indices for them and fewer bits for the quantized signal. So in vector encoder, we're dividing our signal into signal vectors. We find the nearest code word and we transmit its index to the decoder. On the decoder, we read out the code vector from the codebook using the index from the encoder. We concatenate the sequence of code vectors into a sample string. So a very interesting property is that vector quantizers not only give an advantage for signals with memory, but also for signals without memory. In the scalar case, we can sample an any dimensional space on a regular grid, which is given by the coordinate axis of the space. Whereas with vector quantization, we can use something like a dense sphere packing into this any dimensional space, such that we reduce the distance between reconstruction vectors, the so-called code words, and we reduce the expectation of the quantization error in this case. How do we do the quantization in the n-dimensional case in general? So we choose n-dimensional reconstruction values, which we now call code words. And we use the nearest neighbor rule to map each n-dimensional signal vector to the nearest code vector. You could think of it as the neighborhood as n-dimensional spheres around each code vector. So each code vector has an index, and this index is then transmitted to the receiver, which uses the code vector as a reconstruction value. The collection of all code words is called a codebook, and the size of the codebook also determines how many bits are needed for their index. So usually codebooks are fixed, predefined, but there are also some cases which are adaptive code books, for instance in speech coding. And how do we obtain our code book or our code vectors? So basically, like in the Lloyd-Max case, we're just extending it to the any-dimensional case. And for the any-dimensional case, this is called the Linde-Buzo-Gray algorithm. So, and it looks like the following. We initialize the iteration with a random assignment of m any-dimensional code words, y of k, it's a vector. Then using the code words, we compute the decision boundary b of k as the set of all points with equal distance between two reconstruction values, two code words. So then we're using the nearest neighbor rule. And such constructed regions, they are also called the Voronoi regions. Okay? To assign a vector to a specific region, we use the nearest neighbor rule directly. We simply test which code word is closest to the observed vector. Then the next step is using the PDF of our signal and the decision boundary, the Voronoi region. We compute new code words as centroids, center of mass, or the conditional expectation over the quantization areas, the Voronoi regions. So it's the same as in one-dimensional, but here we the integral is going over n-dimensional. Then we repeat. We go back to step 2 and we repeat it until it's sufficiently small, so it's smaller than a defined epsilon. So here we assume that we have a PDF of the signal, but observe that here we would need a multi-dimensional PDF or probability distribution, which is difficult to obtain since the volume of the space increases exponentially with its dimension, but the number of vectors rather decreases. Hence, we get less dense signal points in high dimensional space, which means a PDF is very difficult to estimate. So what we can do, we need a different strategy, and instead of a multi-dimensional PDF, we often only have a so-called training set to obtain our codebook. So the training set is a set of signals which have statistics like our target signals, but which are only used to train our codebook vectors. So we use the Linde-Buzo-Gray algorithm to train using this training set. So to test the resulting vector quantizer, we should use signals which are not in the training set. We can still use the same algorithm as with the PDF, so we just have to compute the centroid or the conditional expectation in a different way. So assume if we have L samples in our Voronoi neighborhood region and we want to compute the centroid for this Voronoi region, we could do that by assigning each signal vector x of k of the training set a probability of 1 divided by L. So we assume each vector is equally likely, and then just use the above formula for the centroid, replacing the integrals by the sums. And this results in this equation here. So this is simply the average of all observed training vectors in our Voronoi region. The sum contains the indices I of signal vectors x of y, which are closest to the code vector k. So this is part of our iteration. After training the codebook with the training set, so we use only for training or to learning the codebook, we have a fixed codebook which we can then use for encoding our data. So observe that the training set should be different from our data. The result vector quantizer could look like this image for dimension equals to 2. So where the blue lines are the boundaries of the Voronoi regions, so they're the b of k, and the red stars are the code vectors y of k, and the green dots are the signal vectors. Let's take a look into this example. So determine the codebook vectors of a LBG vector quantizer for dimension n equals to 2, and the number of code vectors is m equals to 2. After one iteration for 2 vectors with the given training set. So this is our training set, is x, and then we'll have our initial codebook vectors are y1 and y2 given by this. So the training set, we're split this into two-dimensional vectors, so we get 3, 2, 4, 5, 7, 8, 8, 9. So the solution follows the algorithm which we explained previously. We start with the given randomly assigned codebook vectors y of k. The next step, we calculate the decision boundary b of k using the nearest neighbor rule to obtain the Voronoi region. So this results in a set of midpoints. And these midpoints form the Voronoi boundary line, which is perpendicular to the connecting line of two code words. So here is the direct midpoint b of k. So b of k in our case is the line going through the point 3 and 4. And the line consists of all points which have equal distance to the neighboring code vectors. Now we can draw the given training set vectors, the codebook vectors, and the Voronoi boundaries. So observe that the computation of the boundary line of the midpoint is useful only for drawing the picture. Yeah? In a computational implementation, we don't need to compute it. Yeah? We just need to use the nearest neighbor rule. So here is a pie plot. We have here our train set. So we split this sequence of numbers into vectors with two dimensions. So that's what we're doing here. So we will have here this y1, this codebook vectors y1 and y2. It's also defined here. So then we have this plotting here, just formatting to have a scatter plot here. So we have this picture here. So we have the Voronoi region 1 and the Voronoi region 2. So we see here, for example, this is the point 3 and 2. So this is our training set X, 3 and 2, 4 and 5. So we have here 3 and 2, 4 and 5. And we had our code books Y. So we have 1 and 2, 5 and 6, which is given here. And then we're just plotting here the Voronoi region. So we calculate a boundary using the nearest neighbor rule, and we have these two regions here. So the step 3, we have to compute the new code words y of k as a centroid or conditional expectation over a quantization area. That is our Voronoi region. So in order to do that, we use this formula right here. So in order to find out in which Voronoi region a vector is located, we use the nearest neighbor rule, and for that we need to calculate the Euclidean distances between all the training set vectors and codebook vectors, and then we decide which training vectors are closer to which codebook vectors. So we will start with the first training set, and we will calculate the distance to the codebook vector y1, and we calculate the distance to the codebook vector y2, and we see that y1 is closer to the training set vector x1. Then we move to training set x2, we calculate distance to vector y1, distance to vector y2, and we see that y2 is closer. We move to the next training set, we calculate the distances, and we see which codebook vector is closer until we've gone through all the training set vectors. And now we can compute the centroid or the conditional expectation for each of the two Voronoi regions. So we've seen that for Voronoi region 1, we had only the training set vector x1. So its centroid or the new codebook vector is identical to x1, and we get the new codebook vector 1 as y of 1 is 3 and 2. But for Voronoi region 2, it contains the 3 remaining vectors. So what we do, we obtain its centroid by averaging over them. So we obtain our new codebook vector 2 as the average. And then if we update our plot, we see now that the new codebook vector, so This one is moving to this one here. So we are in Voronoi region 1, and as we calculated here, the new codebook vector becomes the set x1, so it moves to here. And for Voronoi region 2, it goes down, the value is 6 plus a third and 7 plus a third, so we have here, it was originally here, so it goes 6 plus a third, and then here we had 7 plus a third, so it moves there, and then we can draw a new boundary line here, and then we go back to step 2, and we'll repeat this procedure until the result does not change anymore. So taking a look into vector quantization in a encoder and decoder system, so both the encoder and the decoder, they have the same code book in their memory. In an encoder, we first convert our signal sample stream to our vectors. Then we map those vectors to the nearest code vectors. Then we transmit the indices of those code vectors to the decoder. The decoder converts the indices back to the code vectors, and the code vectors are then concatenated and converted back into a stream of samples. So for example, in the encoder, and we have string to vectors, vectors to code vectors, to indices, decoder, indices to vectors, and then vectors to the stream of samples. So let's take a look at the Python example for vector quantization in an encoder and a decoder, a complete example. So first, I'm going to load now, it's Iron Maiden Aces High Introduction. So there is this very famous speech. Let's listen to it. So this is the Aces High introduction, and this is going to be our training set. So I'm loading the audio, and then I'm plotting here just the normal waveform, and we can listen to it. But then we are going to convert this into a two-dimensional vector space. So we are reshaping our signal to have two-dimensional vectors. And we see that there's a distribution here in the diagonal. So then we are going to create our codebook. But for that, I'm going to use scikit-learn, the k-means. So we've seen that the nearest neighbor rule is used. And then we are going to use this already implemented library, k-means from scikit-learn clustering. So we are defining a number of bit if equals to 3. So that means that we'll have 2 to the power of 3 clusters. So this is what we're doing here. So then we're initializing our data, our model. We're creating a model using k-mean plus initializer. The number of clusters is defined here, and we define a number of iterations, and then we will fit this model using our training data, which is these two-dimensional vectors here. And then, so now we have our code book trained here, and here just to plot, so we will have here, this is our two-dimensional vectors, and then we have the Voronoi regions and the centroids marked with this cross here. So we just did what we explained previously, but using this very convenient scikit-learn library. So we are using the k-means to, and here we're just plotting the Voronoi regions. So this is how we do it. So we have this very nice plot, and we can see our code book. So we have 8 values, and these are the centroids. Okay. So now we go, we take indices of our code words. So now our coded signal would look like this. So we are using the nearest neighbor rule. So all the vectors that are near to this centroid, they will be assigned these values. So we are doing this mapping. And on the decoder, we decode indices to vectors. So this is what we are doing here. And then I am just plotting to have the decoded signal. So in this case, I'm just showing you how it would sound. This is we're using this signal as the training set, and then when we encode and then we decode, it would sound like this. So we just trained our model to get this code book, and we use this code book. So it's 3 bits, so 8 possible values, and then our signal that used to be this becomes something like this. Now we have already our code book, and we are going to encode and decode another signal using the code book that we got by training using another signal. So we used ACES high speech to train, and now we are going to encode and decode the number of the beast introduction using the learned code book. So both the encoder and the decoder, they would have the same code book. This is what we are doing here. So I'm loading now the number of the beast. We listened to this before. So just for comparison, I'm going to encode using the mid-rise quantizer, so the normal uniform quantizer we've seen before. So I'm going first to use this mid-rise quantizer, and then this is what I'm doing here. I'm creating the mid-rise quantizer, and this is the quantized and dequantized signal. So we can listen, like we see there's a lot of quantization errors we see with the mid-riser. Let's listen.
Let him who hath understanding reckon the number of the beast, for it is a human number, 666.
So we see a lot of distortion here. We're using the same number of bits, so we're using 3 bits for this mid-rise quantizers. But now let's see how it would sound if we use the vector quantization, using those code book that have been trained using ACES high. So this is what I'm doing here now. This is the vector quantization. So we had our code book, and now I'm encoding the number of the beast. So this is the encoded signal. This is what we have the indices transmitted. Now we are decode using the same code book, and then we become something like this. And then let's listen to it.
Let him who hath understanding reckon the number of the beast, for it is a human number. Its number is 666.
We also see quantization error and distortion there, but it looks that it's doing a much better job than the mid-riser.
Let him who hath understanding reckon the number of the beast. Let him who hath understanding reckon the...
So we can also compute the quantization error, and we see that there is a significantly difference into the quantization error for both types of quantizers. So this was an example using vector quantization. So we used the nearest neighbor rule as we did with the Lloyd-Max quantizer, but here we do this training part. We create a code book using this training, And so this is an example of with encoder and the decoder of the vector quantization. So that's it for our notebook.